this computer. Okay, so I'm recording. So as always, thank you very much for joining the course. I think, as I said, I'm really excited of seeing how many of you want to learn from us. So thanks. Today we will cover a different topic. Before starting, I just want to say that my laptop was broke last week, so this is a new one, and I've been testing things, and I hope everything works. But if there are some technical problems, so I just apologize in advance. But I think it's working. So let's hope for that. And yes, and the second thing is that, yes, let me just move one slide. So today we're going to talk about response functions. This is, I think, is a very interesting topic, but is sometimes a bit difficult, even for me. So if I say something wrong, Basilio, just jump in and correct me. And if everyone has any question, just raise your hand or just open your mic and ask them. I will try to go slow as last week, but I know that even going slow, this is a difficult topic. So just ask me any question that you can have in mind. Okay, so the idea is that we will cover how we can compute the response functions, how we can read them, and try to understand what they are. As before, the process is exactly the same for SER and for design. So everything that we do today, if you learn how to do it, then you can also do it in the future for design when you are doing NLT computations. So I think it's worth to try to really understand it and follow the steps. So as last week, I will try to show you how to do it following a very simple IDL script with a lot of comments. And all those things I will share with you later, so then you can try it next week or anytime. And before that, I think this is probably just a few times where I want to, just let me move this. Yeah, one of the few times that I will show you an equation. I will leave more detailed things in the future for Basilio and Han, that they are probably better than me at this thing. But I think today is worth it to look at the equation and try to understand what response functions are. So I will bring an equation from the original publication of SER, that is from 1992. I put the publication inside the folder day 3, that is the folder corresponding to today's class. So you can read it, or you can just check the equation or trying to understand a bit more the different elements. And the idea is that this is the equation. And I will just put a text here. I will try to go step by step. It's relatively simple, but I think it's a bit difficult to understand. So just let's go very slowly. So the idea is that we have that a perturbation delta x on the atmospheric parameter x. So imagine that this is temperature. Okay, so we can say that a perturbation on temperature, that we have it here in the equation, that is done at a given optical depth, so at a given height in the atmosphere. So this perturbation is going to induce a modification of the Stokes profiles, and this will happen at a given wavelength. Okay, so the important thing is that when you change the atmosphere, there's a modification or an answer to that perturbation on the Stokes profiles. And the idea is that the perturbations are done at different heights, but the response to that perturbation is happening in different wavelengths. Okay, so the idea is that this is Stokes profiles, and these are atmospheric parameters. Okay, and the relation between these, so how you can, so the relation between the perturbation and the effect on the spectral information is what we call response function. And as we are relating atmosphere, optical depth with wavelength, so then the response function, it contains both dimensions. So it's a two-dimensional parameter that it has a wavelength and then optical depth. Okay, so the idea is that today we will work on this. And the important thing is that this, I think, is the key of modern inversion codes, and it was the key of SER. In fact, the code is named Stokes inversion code based on response functions. And it was a big step respect to the previous inversion codes, because in this case, we are adding information of optical depth. So it means that for the first time, we are fitting the profile, perturbing the atmosphere at different layers, so we can have information of the stratification of the atmospheric parameters. Okay, so I think this is really important, and it has been the baseline of the modern codes, not only design, but most of the codes that you have nowadays, they are based on response functions. Okay, so then next is homework. So we just stop here, and we can also just let me make this. Okay, so I'm moving the plot. So let's see if I can have it like this, so you can see me. 1 second. Yes. Okay. So the idea is, okay, I will minimize my camera. Okay. So I will send you, I will put in day 3. So here you have the paper. This is the presentation I'm giving, and this is a folder with figures. So later on, I will put this folder that is called RF, or with response functions. And here you have everything that we will cover today. I will make a lot of plots today, but I also made them in what I called high definition. So you have here several plots, and you can open them, and they are in EPS format. So they are a bit more, they are nicer than the ones I will show you. So the idea is that even if you don't want to run the code, you can follow the class, and then you can go to this folder and you can check in detail the plots. Okay. So then let's go to this folder that I will share with you. And here we have several files. And the important one that we will start using is this rf.pro. Okay, so I have it here. And the first thing that we are going to do is to start from a previous class. Just 1 second. I'm trying to play with the. Yes, I think this is better. So the first thing that we will have is that we are going to read the FALSI model, and we are going to put some information in the parameters. So we are defining a magnetic field of 450 Gauss. We have a given inclination, an azimuth, and then microturbulence. And we are going to create an atmosphere, call it init atmosphere, like last week. And then I'm also here doing a synthesis, like it's exactly the same we did last week. So if you run this until this is stopped, if everything goes well, okay, you will see this profile that you have here. Okay, so the idea is that why I'm doing this, and is that because what I said before, so the response function, it will give you information of atmosphere. So I mean the relation between changes in the atmospheric parameters with the impact of those changes on the Stokes profiles. So then you need 2 ingredients before starting. So you need an atmosphere that you are going to use as a reference, and is the one that you are perturbing. And you need also a spectral range where you want to study the response functions. So in this case, we have this spectral range that is the same as the last week, where we have 2 iron lines, and we have also continuum. Okay. So then the first thing we're going to do is to make a similar call as in the previous example. So this is for synthesis. In this case, it's for computing the response function, and it's the same. So we are telling the code, please run the control file called rf.roll with SER. In this case, it's called new, because I added the modifications that we were discussing in Discord. So I will put this new version also in day 3. It's essentially the same, but we added some upgrades, so we can just use this one. But basically it's the same. So calling this control file and call SER with it. So then let's go to the control file. That is this one. So the first thing that you will see that is different is that we have now here -1. So if you remember, we had that, yes, I'm still trying to make, yeah, sorry, that the camera is in the middle. Okay, so you have -1. So if you want to run synthesis, you put 0. If you want to run inversions, you put numbers above 0. So 1, 2, 3, or 4, 5, depending on how many cycles you want to run. And then -1 is for running the computation of a response function. Okay, so in this case, profiles, it's because it was there. So the important thing that you need to have is a wave grid, as we are running the same example as before. So it's calling index 6 and 7, and with this spectral range. So you look at here and you said, okay, index 6 and 7 from this line list. So you go, and 6 is 601 and 7 is 602. Okay, so we are confirming that we are running the lines that we are interested on computing. Then we have the abundances that are the same, and then we have the atmosphere that we just created here. So in the previous step, we created an atmosphere that is essentially FAL, but we added a magnetic field. Okay, so then with this we can run, we can leave this like it is, and then the idea is that now you put either 0 or 1. 1 is for the response functions that you want to compute, and 0 is that if you don't want to compute them. So for example, if you want to compute response functions to temperature, you just put 1 here, then you run the code, and then now it's saying, yes, let me move this a bit up. Okay. So now it's saying that there's an output response function that is called init@.rt. Okay, so we have already computed the response function. The idea is that I wrote here a note. Yes, here. So these are the response functions that you can compute. The idea is that the code will use, yes. So if you are using, for example, init.mod, so this is your atmosphere, then the code will take the first name, and you can see that is here, and then it will add an extension. And the extension is RT for temperature, electron pressure, microturbulence, magnetic field strength, longitudinal velocity or line of sight velocity, inclination, azimuth, and microturbulence. Okay, so depending on what you're interested on, then you will have a different extension. And then as an additional note, so there are no way, at least through the control file, of computing the response function to geometrical height, gas pressure, or gas density. I think this is essentially because it's what we said last week, that the code internally works with the combination between electron pressure and temperature. So these 3 parameters, they were added later on, and they are in fact not used during the inversion. So they are computed after having a consistent atmosphere. They are computed after that. And the same with filling factor and straight line correction. So you don't have response function for those parameters. Okay, so then there's a warning here. So just let me briefly show it to you. So imagine that you said, okay, I want to have all the response functions, velocity, inclination, azimuth, microturbulence. So if you run it with the current configuration, it will crash, and it will say that there's a number of pre-parameters. In this case, it's a combination of optical depth and wavelength that is larger than the current limit of mfit max, that is this one. So if you see this, then you said, what is mfit max? And the idea is that the code where you have the source code installed, it has a given file that it establishes the size, the dimension of different things. And this, in this case, is defined like this, so it will crash. So then one option is to just run it for less parameters, so like this. And you said, okay, I'm going to compute temperature, magnetic field, and velocity. And this time it works. And then you said, okay, now I have this. So I want to do it for the rest, like inclination, azimuth, and I don't know, for example, microturbulence. So then you can do it like this, and you see that it's writing different names. And this, I think, for a simple test, that is most of the cases where you run a response function, it's fine. If you feel that you are going to do it a lot of times, then you go to the place where you have the code and you look for the file parameter and you open it. And here you have that this is the definition of mfit max, okay? And as you can see, it's 256, but in principle, it can be changed. One thing though, that I think I put it here as a note. So the idea is that there are given numbers here, and in principle, you can change them and you can increase them, but the more you increase them, usually a bit slower, the code will go. So if you plan to do a lot of inversions in parallel, these minor modification that will reduce the speed, it will take an impact. And if you are only changing it for computing the response functions, I think it's probably not worth it, but it's your choice. But the most important thing is that if you put big values in all of them, the code will crash, because I think it will complain that there's not enough memory. So you can try to change some of them, but don't go freely and put all of them in a very high value, because the code will crash. But essentially, if you are going to run it just once or twice, you can do it as I did it, that I already have computed all the response functions, and I just change the places where you ask the code to compute it. And in fact, when we will do it in parallel, it will be much easier to just run once the code in parallel for all the pixels that you're interested on for temperature, and then you make a second run for a microturbulence, and then a second run for magnetic field, because it will increase a lot the volume that you need. So it's basically much better to go one by one. Okay, but in principle, if you want to change, or maybe you have a wavelength vector that is really, really big, and for some reason the code complains that it cannot handle the wavelength vector that you are asking, you can go to this file and then you can change things. Okay. Okay, so then let's go back. So we have computed all the response functions. We know now what atmospheric parameters they refer to. So then let's read one of them. So in this case, we're going to read the temperature response function. We will use this routine. This one is an ideal routine. I think in this case, the response functions are not safe as an ASCII file, so they are a bit different. So if you want to read them and you don't use IDL, I think probably Ricardo has Basilio?
No, there are ASCII. Okay. The problem is that it's a matrix that is written like a vector. Then it is a little complicated to disentangle all the information, but it is ASCII. Then you can edit the file. Okay. But it's written like a vector, being a matrix, and then it is ordered in a complex way.
Okay.
In the parallel wrapper, it's going to be saved in a normal fits file, so it should be easier.
Yes. Extract information. Yes. So that is what I was wanted to say. So Ricardo already is reading and interacted with every output SER has through Python. So if you feel that you want to do this same example, but just using Python, probably Ricardo has a way to do it. So you can ask him, or you can put it in Discord, and probably someone has the program to do it. But essentially is that. So if you use IDL, you can use this one. Okay, so then what we are is just defining a name, and then we are reading this response function to Stokes I, Q, U, and B. This is important. So if you remember from the previous equation, we show that perturbation in a given atmospheric parameter will induce a perturbation delta I of lambda, but that I, it was the Stokes vector. So you have 4 Stokes parameters, okay? And then you have also the number of optical depth points and the number of wavelength points. Okay, so let me show you the response function, and then we will cover this text and we will try to understand it. Okay, so if I remove, just let me go back. So we are not going to compute any response function. We don't need this. Okay, so then now I hope you will see. Okay, so we have a response function here. Just 1 second. Okay, so the idea is that you have that the response function, as we said, they are 2D arrays. So in one dimension, you have the spectral domain, and in the other dimension, we have the vertical domain. So this is optical depth, but you can imagine that this is height. Okay, so this is lower layers and higher layers, and this is the same spectral region that you saw before. So we had continuum, then we had 2 lines in absorption in these positions. Okay, so I'm plotting them in this way. So I'm computing the absolute value and the maximum value of the absolute of the response function, and I'm normalizing it through this value. So then the response function will go up to 1, but this is the maximum. Okay, because usually they have lower values, but because it's they are derivatives, so it's yeah. So basically we just normalize them, and you just put here arbitrary units, and usually it's fine. So the idea is white with this color code, it means 0. So then in this context means that the response function is 0, or in other words, a perturbation in a given atmospheric parameter and a given height, it will not produce any change. So in this case, we are examining or checking the Stokes I response function to changes on temperature. So it means that if we change the temperature in very deep layers below the optical depth 1 or the visible continuum, it's saying that the profile will not change at all. So there's no perturbation on the spectral lines. If we move a bit higher and we change the temperature at the continuum, at optical depth 0, that is usually the visible surface, we see that there's a black color that covers all this region, also goes this region, and also this region. So what it's saying is that if you change temperature at this layer, you are changing the continuum, okay? And you see that there's a strong color here. But if you change it higher, then there's no color here. So what it's saying is that your continuum will change essentially with changes on temperature that happens only in this range of heights. If you change the temperature higher, you see that only black color happens in this region and in this region. I think, Basilio, I think your microphone.
Yeah, it's the logarithm of optical depth. In fact, this is not optical depth, but okay, it's okay.
No,
that is
that your microphone is on, and I think I'm hearing piano.
Yeah, my wife is playing piano. No, I was saying that you are plotting the logarithm of optical depth. Yes. It's not optical depth equals 0, it's optical depth equal 1. Yes. Okay, this is the deeper, it's not the upper layers, it's the deeper one.
Yes.
Okay.
Yes, so just let me check, because I think I did it properly here. Yes, here is log tau 500. I think this is a mistake here, but in the nice figures that you can check later, it's log tau. So yeah, it's what Basilio said. So this is the logarithm of optical depth, and so tau equal 1 is this log tau 0. Okay. So then what I was saying is that if you change the temperature in higher layers, the continuum doesn't change, but you see this fluctuation here, or this spike. So what this means is that if you change the temperature at these layers, there's a spectral region that in this case and this case corresponds to the location of your spectral lines that will change. And they don't change when you change it in lower layers. So essentially, spectral lines are sensitive, mainly the line core is sensitive to changes in temperature that happens at different layers than those in the continuum. Okay, so I don't know if you more or less got it. So I hope yes. If not, just ask me a question. But the important thing is that 0 means that the spectral profiles will not see any effect. So it doesn't matter if you change the temperature here 1 Kelvin or 10,000 Kelvin. the profiles will not change, and the same in this region. Okay. So then let's just, for having as an additional example, I'm doing the same, but now I'm going to show you the response function, Stokes B response function to changes on temperature. Okay. So if we do it this way, so now we have that I added a different color table because the intensity is defined positive, but the Stokes profiles Q, U, and B, they can change sign. They can be positive or negative. So the same happens with the response function. And in this case, you see that there's no color in the continuum, and this it's reasonable because there's no signal from the Stokes profile because there's no line there. But you see that there's a similar shape as before, and the idea is that now the pattern is a bit more complex. So I think sometimes even if you try to understand response functions, it could be a bit complicated. So don't feel too bad if you cannot do it. So it's just that some parameters and some response functions for a given parameter, atmospheric parameter, and a given Stokes profile are relatively easy to understand, but sometimes it's more difficult for the rest of the cases. So don't feel too bad if they look so complex like this one. So in fact, I'm going to show you a set case. Yes, and in this case is I'm reading now the response function to field strength, okay, and I'm normalizing them again. So what I'm going to show you is the Stokes V response function to perturbations on the field strength, okay. And now it looks a bit more simple. So the idea is that, again, there's no value for the response function outside the region where we have spectral lines. Okay, and now we have two colors, and then we have a white line here in the middle. So if you try to understand this, it's saying that if you change the magnetic field, for example, at this layer, the lines will show a spectral change. And in the case of the Stokes B, the change will have a sign in this side of the line, and it will have the opposite sign in this side of the line. So I put as a question why you have this change, and I recommended you to try to look at Stokes B while you perform synthesis of using a constant magnetic field like we have in this example, but you change the field strength. So for example, you use 100 Gauss, 300 Gauss, or 600 Gauss. Okay, just as a tip, but maybe it's good if you try to, 1 second. Okay, so, okay.
Excuse me, can I ask, this depends, the sign depends on the field direction. So you say it's for positive field direction, what you show examples. If you change the field direction, then it will be opposite signs, yeah?
No, I think. Okay.
Yes, it's depending on the inclination. It's the same of the direction of the field, of course, yeah.
Yeah. This means that also the red and blue will swap, and then the response will be corresponding the opposite also.
Yes. Exactly.
Yeah, okay, thank you.
Yes. No, what I was going to say is that the difference of sign is basically because of the shape of the Stokes V. So try to understand this. And the idea is that if you increase the magnetic field and you, for example, compared to this atmosphere, if you increase the magnetic field and you run the synthesis again, the amplitude of this profile will go up, and this one also will go up. But this means that this lobe is more positive, and this one in absolute value is larger, but is more negative. So essentially what we are seeing in the response function is that increasing the magnetic field will increase this one and will make this one more negative, and decreasing the magnetic field will make this one lower, so less positive, and this one less negative. So this is the main reason why you see, for a simple example like this one with constant magnetic field and zero velocity, why you see that the response function, they have opposite signs. So yeah, but yes, let's try to reproduce it and make the synthesis with different field strength, and you will see what I mean. And this is only for a small So magnetic fields with a low amplitude, so like between, I don't know, 50 Gauss and 700 Gauss for these lines. When you go up, then the change on the spectral features will be a bit different. So just play, as I recommended you, with 100, 300, 600. Okay, so then let's go back. So we had this, and before I forgot. So just let me put a stop here because I forgot to tell you that I think is interesting. So if we go back, so this is temperature. So I was saying that this is the signature of that we have a spectral line here, and this is the signature of continuum. But you can see that this peak, it goes a bit higher than this one. And this is something that you will see as you practice with the code. So different spectral lines, they have a different height of formation. This is how we call it. And the idea is that some of the lines can be sensitive to changes at a given layer, for example, in the line core, and some lines are less sensitive to that change, or they are not sensitive at all. So it means that if you have only, for example, this line, you're, I think someone has a microphone on and it's whistling. So, so just I was saying that the idea is that if you only observe this line, you are not sensitive to temperature for this given model to this layer. But if you combine it with this line, then you are sensitive. So the idea is that usually we aim to combine as many spectral lines as possible. If those spectral lines, they have a different height of formation, they can complement each other and they will increase your height resolution. So if you have more lines, then you have different sensitivity and different region of height of formation. So in fact, the next thing that I wanted to say before going ahead is that, okay, it seems that this line forms higher than this one. That's interesting. But also here you see in the same scale, you see that the color here is more saturated than this one. So this is also saying you that response functions will give you an idea of how the profile change respect to the perturbation on the atmospheric parameter, but also the amplitude of that change. So in this case, what we can understand from this is that this line is more sensitive to a perturbation on the magnetic field than this one. So then having lines that form at different heights, but also they have a different sensitivity to the atmospheric parameters, it's also very important. So it's good to complement your inversion with multiple lines that they are different in terms of height of formation and also sensitivity to the atmospheric parameters. Okay, and then I think if I do this, okay. So now we have been watching them in 2D. So now let's try to a step further and try to watch them in 1D. Okay, so I put it here, a blue line, a green line, and a red line. I just put them in a tentative location in the wings for the blue and the red for the wings of 6301. And then the green one is the zero wavelength. It's a rest wavelength, and we don't have velocity in this atmosphere in this example. Okay, so okay, that's okay, yeah, that's fine. So then we can jump these two, and we are going to go here. So in this case, we are going to make a plot of optical depth versus response function at a given position. So the response function, this is a wavelength, and this is optical depth. So we are fixing the wavelength, okay? And they are at 3 positions that I put here. Sorry, here. So it's a blue wing, line core, and red wing. So then the plots that I'm going to show here is blue wing in blue, red wing in red, and the rest wavelength in green. Okay. So if I do these, okay, you have it here. Okay, so please try to follow what I have done. So we had 2D. wavelength and optical depth, and we have fixed wavelength. So now we have a 1D plot. And I put now the optical depth in this direction. So this was the vertical axis before. So this is lower atmosphere and this is higher layers. And this is now amplitude of the Stokes V response functions to changes in the field strength, okay? So what is saying this plot? So it's saying that in this particular atmosphere, the wavelength that we picked as a reference wavelength, it's showing no response to any change on the field strength at any layer, okay? Then if we move to the wing, it's saying that this wavelength that we pick will show a perturbation when a spectral perturbation when we modify the atmosphere between this range, okay, with a peak here. But if we change the atmosphere in this region, this spectral wavelength position will not change, and the same in this case. And in the opposite side will be the same shape because the line is symmetric. And it will be the same, but just with opposite sign, okay? So then it's essentially what we have before, but just fixing one wavelength, okay? So I think if there is any question, just let me know. If not, just let me try to show you what happens when you put all the wavelengths. So now
I have a question here.
Yes.
So
Yes.
this response function corresponds to certain range of perturbation parameters and the step. Is that defined somewhere, or like how can you say what amount of Stokes V is changed corresponding to 10 Gauss change?
Yeah, Basilio, I think these are analytical response functions, and
this is a change in the unit. I think that when you are changing, for instance, 1 Gauss or
Yes.
1 centimeter by second in velocity or 1 Kelvin in temperature, how is the amount of change in the Stokes profile? Okay,
Yes.
then you are supposing you are taking the derivative, but you are considering that a change in the units in which you are taking this parameter. Okay, if you are using Gauss, for instance, we are using CGS, then we are using Gauss, then this is the answer, the response of the Stokes V profiles in this case for 1 Gauss in this in each interval in optical depth.
Yes, I understand that, but I mean, are there values that you can read this, because you normalize this function to maximum and then you lose all the information?
Yeah, but this is only for the plot that
Yes.
Carlos has done.
Yes, the idea is that if you don't normalize, you have it in the inverse of the unit that you are interested in. So yeah.
It's in the table somewhere, you can read those values, yeah?
Yes, if I don't, so yes. So I think if I do this, it will show, just 1 second. So you see, 1 second. You see that the units are something like -5 or something like that. So these are I think the inverse of Gauss, right, Basilio?
This is per Gauss, yeah. That's what I was like, per 1 Gauss, per 1 meter per second, yeah, this fixed somewhere.
Yes.
Yes. The perturbation produced in the Stokes profile by a change of 1 Gauss or centimeter by second, so on.
So
and
it's
temperature 1 Kelvin then, or what?
Exactly.
So it's always 1, Basilio?
Yeah, because it's a derivative, then you are using the units.
Okay.
Yes, okay, thank you.
So then, Svetlana, I think your question is that if imagine that you want to see how impact will be a change of 10 Gauss, then you multiply this by 10.
Yeah, I just wanted to know per which unit is that.
Yes. Yes. Okay, thank you. So then let's go back. So I said we saw 1 wavelength. So now let's try to see all the wavelengths. Okay. So yes, let me make this up. So the idea is that now it looks a bit more complex, but just let me try this one. Okay, so I will bring this one here. Okay, so we have that before just a vertical cut is just one line. But now if we put all of them, it looks like this. And then what we are seeing is that, imagine this region. So you see that the blue color goes basically from this height to this height, and then it's 0. So these are these wavelengths that go like this. Okay, then as you get closer, then they become like this. Okay, like this. And then basically where we picked the fixed wavelength region is this one, that is the one that is larger. And then as you move to the line core, you will see that it's basically only from here to here. So are these ones that you can see that they are 0, and then it goes like this, and then this one in fact goes like this. So it's only sensitive to this region. But the important thing is that if you take like the equivalent to this, you are basically saying that this line that was dropping here, it's complemented with other wavelengths that are dropping here. So your height resolution, so the more wavelength points that you have, the more lines that you will have like this, and then the better high resolution you will have for different parameters. Okay, so it's important, as I said before, to combine different lines, but it's also beneficial if you have different spectral positions along the line, because they will change not only with a different amplitude, like this case, but a different height. So it's also good or extremely beneficial if you can cover the lines with several spectral points. Okay, and for this reason you have this combination of lines. Okay, so then let's go back to this example. And okay, I want to move to uncertainties, but before going there, is there any question that you have now about this or something that I said?
I have a comment again. I'm sorry.
No, it's fine. It's fine. It's good to.
So this is
questions.
for the fixed, like for the fixed B also. Like if you change B, then of course the profile will be completely different and perturbations will be different. So
yes.
That's also important.
Yes. 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 We can just quickly check it. So imagine that. Let me try. For example, if I said, okay, I don't know, 2000 Gauss. If I do this, it changed a bit, but maybe we can put a velocity. So it's changing a bit, not so subtle. Maybe if I put a gradient here, it will be better. But yeah, basically this a nice plot with. Oh, sorry, it went too fast. This nice plot where the wavelength, the rest wavelength is completely 0 and everything is symmetric respect to this wavelength is because I
think you are not changing. You are not running the program, writing the response function. Then you are changing the model, but not running the program.
Yes.
Then.
Sorry. So again, then let's try. So 2000, and then let's put 5,000 kilometers, and then let's run for field strength. Okay, so field strength 1. Thanks, Vasilio. I thought. Okay, so then we have a profile that is now very different, and I wrote the response function, and then let's go like this. Okay, so now you can see that in fact some of the red lines, they go here. Some of the blue lines, in fact, they are here, but probably below the color. And as we have a velocity, the 0 wavelength now is not 0. So probably the 0 will be at some point. So yeah, so if you change the atmosphere, it will change. And if you add gradients, this will be much more complex. So was this your question, Svetlana?
Yeah, in principle, yes. But for B field, if you don't change atmosphere, but change the B, then it changes as well, because lines get split. Sorry, my phone is running.
Yes. Yes, yes. So I only change. Well, I could just not change the velocity, but basically now we see that this mix of spectral, sorry, yeah, of lines, because the line is split, so it's showing a different the decimal pattern. So it's a bit different. Just let me run. Okay, so yeah, so it's important that if you want to study response functions, you should study them with a reference atmosphere that is similar to the one that you are interested on. So if you are interested on white sun, or if you are interested on penumbra or umbra, then you should try to look for a representative atmosphere of that scenario, because it can be very, very different, the result. Okay, so let me see where we are. Okay, so we are here. So then any additional questions? Okay, so until this point, I hope I show you more or less what are response functions and why they're important. The idea is why they are key for the inversion code is because the code will try to perturb the atmosphere at a given node location. We will see this in detail next week, but the idea is that the code will perturb the atmosphere. And the code will do it based on the response function. So the code will compute response functions, will try to see where the spectral lines are sensitive to that to perturbations on the atmosphere, and then it will change the atmosphere there to try to reproduce the profile that you want to fit your observation. So the response functions are the key of the inversion process. So they are the way the method has, or the inversion code has, to know where it should change either temperature, either magnetic field, or azimuth, to try to fit the full Stokes profile. Okay, so we can say that is basically the cornerstone of the code. Okay, so then now that I think you know that they are important, I thought that it would be nice also to add something that is purely related with response function, and it's something that we sometimes use, but we don't know exactly how it comes. So I will try to show you how the code more or less estimates the error that you will have in your file. So you will have an estimation of the error when you have a fit. It will tell you in which regions the atmosphere has a larger or a smaller error. And the idea is that this error, it's basically an uncertainty, and it comes from the response function. So let's try to see more or less how the code does it. And I think it's slightly different, but probably Basilio will. Okay. Okay, we have a question. I don't know if you see the chat. If not, I will read it. So Harsh is saying, does SER calculate response functions before every iteration? And are these analytical response functions? And I think the answer to both is yes. So the idea is that the code, if I understand correct, it computes every time it changes the atmosphere, it computes again the response function to know where it should go in changing the atmospheric parameters. And in the case of SER, it's always analytical response functions. And in the case of desire, it's also analytical response functions, but they are weighted with departure coefficients that we will see later on. But in both cases, they are fully analytical response functions because they are LTE response functions. Okay. Okay, additional questions? Yeah. Okay, so. Okay, so Basilio is saying yes, and at the same time we integrate the relative transfer equation, we are evaluating the response function. Okay, so then let's try to see more or less how we get the uncertainties. So I wrote here, this is an estimation of the error, and it's, I think this is important. So you always get the estimation or the uncertainty, and this depends on your configuration. So it depends on the atmosphere the code obtained during the fit. it depends on the Stokes vector that you are using. So, and also it depends on the spectral lines. So if you fit the spectral lines with a different atmosphere, your response function will be different, and then your sensitivities could be also different. And at the same time, with the same atmosphere but changing spectral lines, also the response functions will be different, and then consequently their sensitivity will be also different. So always take that on mind. So we need both atmospheres and spectral information to really understand response functions and also having that sensitivities. So let's try it for this example again, 601, 602 iron lines. And what we're going to do is, in this case, we are going to take the response function to temperature. So we read it, and just for purposes, I'm going to normalize it again. And the idea is that I'm doing a loop in IDL, and I'm computing for each optical depth point. I'm computing the maximum for all wavelengths of, in this case, Stokes I, Q, U, and V. So imagine in this example, so this is Stokes V, and this is response functions to B, to the field strength. So I'm computing the maximum at edge height for all wavelengths. So for example, in this case is 0, but in this case will be this line, in this case will be here, in this case will be here, in this case will be here. And I'm not really thinking about which wavelength is. It's just the maximum of all the wavelength. And I do this for Stokes I, Q, U, and V. Okay, so let's see the plot of this computation. So in this case is temperature. Okay, yeah, just let me try to make this bigger. Okay, it's in the nice plot. It's okay. Here it just got over this, but just Stokes I is red, Stokes Q is orange, Stokes U is green, and Stokes B is blue. And the idea is, when you compute this maximum for all wavelengths and at different optical depths, this is what you get. Okay, so it's telling you that if you could have the spectral region that we are synthesizing, you are observing this spectral region with the same conditions that we have, the sensitivity of the spectral lines to temperature, for example, the Stokes I, will be all this range, combining all these wavelengths. And we have that this is basically the continuum that we saw before. And then we have a drop, but then we have an increase again, and we have two peaks. And I think this is essentially the peak of one of the lines and the peak of the second line that we saw that they form at different layers. So you have that you are covering temperature very well. So the response function doesn't drop at any point. And it corresponds to different parts of the spectral line. But basically, you can assume that you are sensitive to temperature in all this region, and then here it drops. So with this atmosphere, then your sensitivity will be smaller here, or basically none. Okay, okay, Svetlana. Thank you, Svetlana, for the questions. And I hope to see you next week. So the idea is that then we have similar behavior for Stokes V with this blue line. And then it's basically the same for Q and U. But you can see that now the amplitude is very different. So they are normalized to the same value, that is the Stokes I response function. For this reason, we have 1 here. But you see that if you compare them for this specific model, and I would say in general, but just keep in mind for this model, Stokes I is much more sensitive to changes in the temperature than the rest of the parameters. Okay? So let's try to see what happens with the magnetic field. And in this case, let me confirm that I'm using the correct response function, not the new one that I computed for the test. Yeah. So in this case, I'm doing the same. So I'm computing the maximum value for a given optical depth over all the wavelength. Then I move to the other optical depth and then all wavelength, and then like this, and I cover all the atmosphere. And I do it for the 4 Stokes parameters independently. So then in this case, when we compute the maximum response functions to changes in B, in the field strength, now is the blue line that has a larger amplitude. And you can see that it's not so sensitive as before. Before we had a peak here and then it was extended. So we have that they are mainly centered here, but still you can say that probably you are sensitive to the magnetic field in all this region with good accuracy, and then here it's already dropping. So this is also something interesting that you can try to play with and try to understand a bit more. You will see that different atmospheric parameters. So Stokes profiles, they show different sensitivity to different atmospheric parameters, and the largest amplitude sometimes changes. So in the case of temperature, we saw that Stokes I was the most sensitive. In the case of field strength, we are seeing that Stokes V is the most sensitive. And if we go and we do the same for the azimuth, let's just keep an eye here. This is the azimuth. So if we do the same, now you will see that it makes sense to observe also Q and U, because it was before they were very, very low. So someone could ask why you need Q and U, but now you see that if you are checking the sensitivity to changes on the azimuth, they are much larger than than I and V. So in other words, if you really want to cover all the atmospheric parameters, temperature, velocity, and the magnetic field vector, you need the 4 Stokes profile. You need to have them well covered with a good spectral sampling, and if you have additional spectral lines, then it's much better because you can expand this coverage. Okay, so now we are seeing this as the maximum as the response function, and then let's try to reproduce what a desire or a SER is going to give you. So now I have again the maximum of I, Q, U, and V, but I'm adding this max RF, max response function, and it's essentially I covered for a given optical depth all the wavelengths, and then I'm telling, and from the 4 Stokes parameters, tell me which one is highest. So I'm now not differentiating the different Stokes parameters, because basically when you're doing the inversion, you try to fit the 4 Stokes parameters at the same time. So then what I'm going to show you now is the, let me see how it looks. Okay, so then I'm showing you in black the temperature, and then I'm showing you as an error plot the temperature, and then these bars, the amplitude of these bars corresponds to the inverse of this maximum response function. So if I go back, yes, let me put here this to try to do it slowly. So if I go back, if I divide something by this value, the error will be really high. And if I divide something by this value, the error will be much smaller. Okay, so what I'm showing you in this plot is that for temperature and for this specific atmosphere, the uncertainties that the code will give you will look more or less like this. So it will tell you in lower layers, the response functions are basically 0. So then your uncertainty is too large. Then the response function is high in all this region. So then your uncertainty is small. And then it drops. And as it drops, then your uncertainty starts to increase. Okay. And then here the uncertainty is very large. Let's try to do the same with magnetic field. So
Hello, I have
yes.
a question.
Yes.
So in the previous one, you showed one Stokes Q and U response function.
Yes.
So this, I think Stokes U was double peaked and Q was single peaked. So what could be the reason for that?
No, sorry.
Just the previous.
The previous one. Yes, this one. Sorry. So
yeah,
you
this
mean
one.
Why these two?
Yeah, why double peak and single peak?
Yes, I don't know, because here we are combining the two lines. So
yeah, it's because you have two lines. If you run the code just for one line, you will have one peak.
yes,
right,
but Dato is asking why we
one
have one in U and two in Q.
Exactly, that is the question.
I don't know. I don't know.
Complicated thing.
Yes, yes. I would need to plot the. Well, we can do it. So.
Possibly depends of if you have one lobe in Q and U, because depending on the inclination and azimuth, you will have one lobe in Q or two in U or the opposite, and this is changing with.
Yes. So I think this one. So SQ. Yes. So this is what Vasily is saying. So depending on the shape. Sometimes you can have one lobe or two lobes, and you can see it here. So the response functions to Q, it has this positive, I think this is negative. Just let me put a bar and the car size big enough. So black is negative and white is positive. So you have that here is changing, but the response function for Stokes U, it's different. So it's smoother and we have just one sign here. So I'm not really sure why, but we can check it just looking at detail. But is in this case for this example, the response function of U, it's like this, and I think it's. I don't know if this is the profile. I would need to check, but I think it's because we have two lobes in this one and in this one. We have two and then it's negative. So I don't know. I don't know. I need to think about it, but yes, maybe I could separate first one line, and then if with one line we also see the same behavior, I will need to check. But it's something that is a derivative. So for a given atmosphere, it can look a bit complex.
Right.
But thank you for the question. Yeah.
Right.
So then I was here. Okay, I think I'm at the end. Yes, let me go. Second. No, I think I need to remove this stop. Okay. So this one here. And then, okay, so now the same for the field strength. So we have that we are using a constant magnetic field of 450 Gauss, that is the black line. And now we are putting as an error the inverse of the maximum of the response function. So you remember that the response function for field strength was like a Gaussian. So we are seeing this. So in this part, the sensitivity drops very quickly, and here it's out of the plot. So what it means is that it doesn't matter what the code is giving you here. You should not trust this part. And the same here. So if the code is doing this, or is putting the magnetic field going up, or is just doing it like a wave, it doesn't matter, because it's telling you that the spectral lines are not sensitive to that change. So it means that you should not try to understand or explain what is happening there, because it's out of the region of sensitivity of the lines. But here you can say things because it's telling you that the lines are very sensitive, and it doesn't matter of how the atmosphere is. So in this case, it's flat, but you can see that the density is very different between here and here. So if you have an atmosphere that do something like this, or it's a gradient or something like that, the important thing is that these error bars that you can obtain from SER and of the inversion, they will tell you how much you can trust the atmosphere at a given height. And here you can trust, and here you should not trust. Okay. So I think that's more or less all. Please, before I forget, just to check the lines in this folder. I mean, check the plots in this folder. They are much nicer. And if you want to compute them, I can also give you the programs. I will not put them because I think most of you don't use ADL, only just old people. But if you want to have the programs that I use for creating these plots instead of this one, I can also give it to you. But what I will share with you is the one for the class today, and then the figures. Okay. So is there an additional question? Okay, something in the chat. Okay. Yes, so I will read. So can you read the chat when I'm sharing, or should I read it? Basilio, for example, are you?
Yeah. I'm reading.
Okay, so then the answer is yes, Ryan. Well, I will read it. So I will explain it next week. But the idea is that you can put nodes that are the locations where the SER code is going to perturb the atmosphere. And the idea is that in the SER version, originally the nodes were located in equidistant positions, but both in SER and desired, it can be. Basilio, can you mute 1 second?
Oh, sorry.
So in SER, in I think in the newest version of SER, but definitely in desired, you can check. You can change the position of the nodes. So, for example, if you go to this atmosphere, so originally, yes. So originally, if you have 2 nodes, one will be in the top, and then in the bottom, and the other one be in the top. If you have 3 nodes, one will be here, one will be equidistant in the middle, and the other will be here. And then as you increase, it will be the same. But with Desire, you will be able to change the location of the nodes. And if you want to have more sensitivity of nodes on a given height, you can do it. And if you want to have sparse location of nodes in a different height, you can also do it. But I think this is something that I will enter in details next week. And then when we enter with Desire, I will also explain it again. But yes, the answer is yes. Okay, so Ivan, I will explain it next week, and I will share with everyone a program that if I do nodes 52, it will tell you how many nodes SER can use. So if you have 55 or if you have 56. So the idea is that I will show you with a program how can you optimally define your atmosphere with a given number of points, and how much combination of nodes you can have. Okay, I think this was your question, Ivan, or your comment.
Sorry, I got the call immediately as I asked the question. My comment was that the nodes have to be on the grid. So if you, for example, have 6 nodes, you need to have 5 times n plus 1 or something like that points in your atmospheric grid. So
Yes.
there are some magic numbers like 61 for which you have various combinations of the nodes, but there are some very ugly numbers like, I don't know, 42,
62 or 63.
Yeah, or something like that. Yeah, which are not going to yield a big success.
Yes. So the idea is that I'm already preparing the next class, and the first thing that I was thinking to start the class with is picking the right atmosphere for the inversion, and it's not only how you define it, it's also the number of points. And I was going to share the program that I'm showing in the terminal, that it will tell you what you said. So if you have 60 points, then you can only choose 1, 2, or 60 nodes. But if you put 61, then you have the possibility of having 1, 2, 3, 4, 5, and up to 61. So I will explain that in detail. And yes, I think it's annoying and dangerous, because sometimes you pick an atmosphere and you are putting a lot of nodes in the configuration file, and basically you are not using them. So this is something that I will definitely work on, emphasize next week. Okay, so next one, because there's a lot. Okay, Angel, so if I understand correct. Yes. So the uncertainties will be the ones of the final atmosphere. So the idea is that if the code does an iteration, and imagine that it goes far from the one that it's better, then in the next one, it will try to get closer. So the important thing is that usually, and I think it's 100%, the last iteration is the most accurate one. So then it will be the one that gives you the best atmosphere. So then your uncertainties, that the uncertainties that you can use should be that of the final atmosphere. But the truth is that in every iteration, the code will give you the atmosphere that has obtained and the uncertainty. So if you want to read the uncertainty, that is basically the inverse of the response function, for each step of the inversion, the code will give it to you. So it will give you the atmosphere, the profile, and the error or the uncertainty for every iteration. But usually, as you are increasing the freedom for fitting the atmosphere, so improving the capabilities of the code for obtaining a good fit, usually the last atmosphere is the one that we pay more attention to. But in principle, everything is on the folder. So I will show you next week, but basically you have all the uncertainties for all the iterations. Okay, so okay. So Basilio, or even did I say something against what you have said? Because I'm now not sure.
No, it's okay. It's okay. It's pretty good.
Okay.
Pretty good. The question of Angel and also the Ivan explanation. It's okay. I want to add that you can always evaluate also the response function at the nodes, because you have explained how to evaluate the response function at each layer, but the code is working at nodes. Then you can put, instead of 1 in the value of response function, you can put other number. And if you, in the first line, put minus, I think it's minus 10, then the code is writing the response function at the nodes. But okay, this is...
okay. Yeah. Yeah, okay. So you mean in this file?
In the first line, you write minus 10.
Okay.
And in Chepra, you can write 5 nodes, and then the program will write the response function at these 5 nodes.
Okay.
Are not exactly the same that the response function of every optical depth evaluated at this node, because it's integrating the information between nodes. Okay, it's something technical, but it's okay.
Okay. No, but thank you. Okay, so then before going back to the presentation, any additional question regarding all these steps? Okay, so then
I do actually have a quick question. Sorry.
Okay.
So I joined late because daylight savings is stupid, and I thought that UK time was universal time. So sorry, my bad. But my question was, are we still talking about just Sir here, or are we talking about the desire that's supposed to be able to handle up to the chromosphere? Because like, how well would this this code deal with say the steep temperature gradient at the base of the chromosphere?
So I think the first question is, we are still with SER, but I think all the process that I have explained for computing the response functions and how you can obtain the uncertainty is the same for SER and Desire. So everything that we covered today, it can be applied for Desire. Regarding your question, I think as we are still with SER, if you agree, we can leave it for the time when we start with Desire. But basically, I don't see a problem with the steep rise. So what I mean, I think, so why you think it could be a problem for the code. So I'm not sure.
I think maybe you have a problem. You will need to have lines that are sensitive
Yes,
to this sound. If you have some line that is forming or having, I don't know, showing a high response in this steep zone, you don't have problem. But it is difficult to find that. You can find coronal lines, or you can find chromospheric line. In the transition region, I don't know, maybe. There are additional problems depending on, because we are evaluating an approximation of the profession, but as Carlos is saying, we can discuss this later. The other thing is that, in fact, British are the owner of Greenwich, then the universal time is United Kingdom time.
Okay. Okay. So Ryan, I think, so let me just briefly say what I was thinking. So the idea is, I think the main problem for being sensitive to a given atmospheric parameter and a given layer is not the code itself, it's the spectral lines. It's what Vasilii was saying. So if you see the plot that I have here, the sensitivity is really bad here. But if you add, for example, calcium 2 infrared 8542 line, or you add some upper photospheric lines like magnesium 1B or sodium 1, then the sensitivity here will decrease a lot. So then I think the key is not the code itself, although when we were there, when we will reach desire, we will explain the limitations that the code can have. But essentially, the reason, so the option for reducing these bars, it doesn't come from the code, it comes from the spectral lines that you observe. So if you have spectral lines that are sensitive to these regions, then your sensitivity will be much higher. And for this reason, sometimes we combine calcium 8542, sometimes helium 1030, sometimes magnesium, sodium, or calcium H and K, because those lines, they are sensitive in these regions. But you combine them with lines that form here, like these photospheric lines. So then your sensitivity is relatively low in all the layers until some point. But it's basically dependent on the spectral lines that you choose.
Yeah, I guess my question was more because I actually tried doing some inversions with a previous version of Desire a couple years ago, and I distinctly remember some very bad experiences trying to get the code to play nicely with a initial guess atmosphere that has any sort of significant sudden transition from the temperature minimum to the chromospheric temperature rise.
Okay.
Like,
so yeah, let's check it when we reach the point. Let's try to repeat the same test that you did, and let's see if the new version is better. Otherwise, we will work on it. But I hope that there were, of course, if it was a previous version, mainly a few years ago, we have really improved it, and hopefully now we will not have these problems. But if you have the same test, then let's try to run it. When we reach this point, let's try to run it and at least double check that we have solved all these limitations. Okay, additional questions? Okay, so I will go back to the presentation and I set homework. So basically, like before, I recommend you to try to run all the tests I made and try to understand. I think it's good if you try to change the atmosphere, because I picked a very simple one, but you can try to add a gradient, for example, in the field strength or in velocity, that it will change the symmetry between the Stokes profiles, and then you will see that the response function changes a lot. But it's important that even if the response function change, probably the regions of very, very low sensitivity, they will not change too much. So we cannot fix that, but sometimes they can be shifted a bit. So the response function could be with a bit higher sensitivity in one layer or in the other. So try to experiment a bit with representative models of your research interest, and try to understand more or less how they work, because it's, as I said, is the main element that defines SER and also desire. And I think this is also interesting. So compare the response function between spectral lines. So, for example, you can compute the maximum of the response function, but just picking. So, if you have the two spectral lines, like in this case, so just take one spectral line and the other, and then compare them. And then after that, you can add more lines. So, if you see the line list, there are different lines like this one or this one. And this could be interesting because sometimes you have an instrument or you have an observation that it comes from a specific wavelength. It could be in the infrared or in the visible or in the blue. Or sometimes you are preparing a proposal, like for example, for the KIST that you can choose. And you said, okay, maybe I want to observe in this arm a given spectral line. So then I have only the option of observing, I don't know, in the visible or in the infrared. So then it's good to have some candidates that are really good for your research interest, for example, magnetic field sensitivity in that range. So in this case, what I'm saying is that this pair of lines, this 152 and this one in the 1.5 micron, they are very famous because they are really, really, really good. Ideally, one would like to complement them, observing all of them together, but sometimes you have to choose one or the other. And it's interesting to check that some spectral lines are sensitive to the atmospheric parameters with a very high sensitivity, for example, magnetic field, but the peak of this sensitivity is not always at the same height. So some lines are sensitive to lower layers, some lines can reach higher. So it's good to know what are the tools that you are going to use for inversions and then for trying to understand the process that you want to study. Then the same, so try to give it a thought of what we are saying by uncertainty. So if the response function is 0 or very low, it means that your profiles doesn't change even if you increase, I don't know, the temperature 1000 kelvins. So then it means that the model that you have there, even if the code retrieve it, you should not trust it. So just give it a thought and try to understand that. And as I said, it's also important because when you see papers with different codes, with modern codes, they usually also try to show some error or uncertainty, and usually it's related with that. So usually it's related with inverse of response function. Not every time, but most of the cases. So if you get a feeling of that, then you will know more or less what are they meaning when they talk about uncertainties, when they show results. And yes, for next week, we will synthesize 1 or 2 profiles. We will embed them. I will explain you some of the things that we were saying at the end about the nodes location, and weights and other things. Then I don't know if we will have time, but if we have time, I will try to inverse also observed profiles, because in the previous case, you can really compare with the initial atmosphere, so you know if you're doing well or bad. But when you have observations, then there's no true answer. So you have to trust more or less what you get. So I hope that with the first step, you will see that you can trust more or less there. And then with the second step, you can say, okay, I trust the code, then I will trust the result from observed profiles. I will probably use Hinode profiles that are the same lines that we have been working, and they are very famous, and you can have the data, you can download it any day and any time. I will show you how to do it. And the idea is that it will be also observed in, for example, in the KISS cycle 1 proposals, it was offered to observe with VISP 601 and 602. So it's good to have an idea of how you can embed these type of lines. And then just probably next week, in 2 weeks, we will work a bit on transforming atmospheres and try to know how to do it. And the good thing is that as soon as you get the feeling of how you can do it, what units, convention for signs and other things, as soon as you get that, then you can do it with any atmosphere, if you are focusing in the photosphere. So then I will try to spend some time here, but you will see that it's very useful, because as soon as people give you an atmosphere, or you have it, or you have developed, then you can run it and then compute, put it in the proper format for running then the Stokes, the code to make synthesis. So then before open for more questions. So next class, I think is programmed for 16. For me, it's fine. I think we can keep every Friday if no one has really strong objections. So then we will meet in next Friday, and I think I will stop sharing. And I think now we can have questions if something was missing, or if you want to add or check, just let me know. And if you want that I share my screen again because you have questions, then I can go back. So please let me know if you want to ask something. Okay, I think 90 minutes is enough. So so people don't want to have any questions. So okay, so then I believe there are no questions. So thanks again, everyone, and I hope to see you next week. And again, I hope you're enjoying the course and learning. And please, if some question appear or some technical problem appear, write it down in Discord, and we will try to help you. Okay, so thank you very much.
Thanks, Carlos.
Thank
you.
you.
Carlos. Bye now.
Bye.
Thank you.
Bye.
Bye.
Thank you. Bye.